Okay. Hi everyone, and so uh, I asked you guys whether you have a question or not. You said no, right? Okay, so let's start the session. In this session, we talk about the last algorithm, materialistic algorithm that we are going to cover, and then we'll move on to game theory. Okay, so this method is called Nelder-Mead simplex method or Nelder-Mead method. The Nelder-Mead simplex method, or simplex algorithm, also called Nelder-Mead method, was proposed by John A. Nelder and Roger Mead in 1965. So the name of the algorithm is named after its authors, right? And it is used in F-min search of MATLAB. So let's Google it. MATLAB F-min search. It's this, okay? So this function f-min search gets some function as input and some initial value, initial solution, probably. So I think initial might be optional. And then it optimizes that cost function for you. So, and of course it minimizes that because it's called f-min search. So f-min search is using Nelder-Mead simplex method. And this is a materialistic optimization algorithm. That's why it's called search, right? It is searching for optimization. It's not a classical optimization algorithm. And let's go back to slides. So its idea is this. First off, why is it called simplex method? First off, don't confuse it with a simplex algorithm for linear programming. Have you heard of linear programming? No? Yes? Okay. So linear programming is, I think in preliminaries, we talked about it briefly. So when the cost function is linear and the inequalities also, inequality constraints are linear, then the whole thing is linear, right? The constraints are linear, the cost is linear. This is called linear programming, and that's a convex optimization problem. Then one of the techniques used for solving linear programming, so there are several ways to solve linear programming. One of them is simplex algorithm. Simplex algorithm for linear programming, not this one, is like this. Do you agree with me that, can you tell me what in linear programming, how is the feasibility set looking like? How does it look like? What? Do you remember inequalities in, let me add a page. Do you remember inequalities? So for example, do you remember we talked about it in the preliminaries? Assume this is an inequality constraint, says that I need to be here. This says I need to be here, right? And another inequality constraint might be nonlinear, such as this, right? With this, what is the intersection of these three inequality constraints? It's like it's here, right? So the feasibility set here is here, and among these points in this feasibility set, I need to find my solution, right? You remember? We talked about it. So now, I'm telling you that in linear programming, all of the inequality constraints are linear or hyperplanes. In 2D, they become line. So what happens to the feasibility set? What shape does it have? Is it circle? The feasibility set is circle. Can you tell? Is it curvy? What? Curvy. But I'm saying that the inequality, so these are inequality constraints, right? But I'm saying that inequality constraints in linear programming are linear. So what do I mean? Like this, right? This. So assume these are inequality constraints. It becomes like this. So what is this? It becomes like a polygon. Polygon in 2D. in higher dimensions, we call it polyhedron. Okay, and we also, if you consider this, generalize this to higher dimensions, it's also called simplex. So simplex, you can see it as a generalization of triangle. You know, this is triangle, right? In 2D. Triangle in 3D is what? A pyramid. Thank you. Right? A pyramid. We can have triangle in 4D, in 5D, in fifth dimensions, and etc. As you see, in simplex, the edges are all hyperplanes, right? As a result, the feasibility set in the linear programming becomes like a simplex, right? In 2D, this simplex is can be like this, not necessarily triangle, but I'm saying it will be a polyhedron in general words. That's why the algorithm used for solving linear programming is called simplex algorithm. And what's this idea? Can you tell me? So assume my cost is increasing in this direction. Can I say in linear programming my cost goes like this? Goes up and down and up and down? No, why? Because the cost is linear, right? So it's either always monotonically increasing or decreasing or not changing, something like that. So it's always like this or going down, right? Now consider a polyhedron and some cost over that. For example, like this, a polyhedron and some cost going up like that. I know that I should find my solution in this feasibility set. Currently, I'm talking about linear programming. Can you tell me where the solution should be? Can the solution be here? Assume I want to minimize the function. Okay, minimize the cost function. Is the solution here? No. Why? Because still here I have a smaller cost. Let's go down, down, down. Where is the solution in here in this case? Well, which one? The horizontal axis, this one, but here I'm out of the feasibility set. The point here, right? The point. So basically, because the feasibility set is a polyhedron and the cost is linear, my solution must be in one of the corners. Do you agree? Yes. Why is it? In one case, it might be on the line. So for example, like this. The cost is exactly perpendicular on that. And all of these points are solution. Right? The cost will be the same for them. But if you rotate this feasibility set a little bit, then this corner, for example, will be the solution. Right? Did you understand? In linear programming, you have a simplex or polyhedron, whatever you call it, feasibility set, and some linear cost. Of course, the solution must be one of the corners. Even in this special case, this line has two corners. Both can be the solution. Right? Agreed? Now, put yourself in the shoes of the designer of the simplex algorithm for linear programming. Yes. This one. This one.
Yeah. Is that?
Now, this line is the cost, and it's linearly increasing. Because I can be any point in this feasibility set can be the solution, right? Do you agree that the solution must be in the feasibility set? Must satisfy the constraints, right? So any point in this feasibility set, when I say in, it means in or on the border. In the feasibility set is a solution, right? Then which one? Is it the solution? No, because here has lower cost, here has lower cost, here. But is it the solution? No, here has lower cost, here lower cost, lower cost. Is it the solution? No, here has the lower cost. What? Why? No. The cost, see, this is a 2D space. And consider on this 2D space, I have some cost. So you can see the valleys and mountains as the cost in this 2D, right? But here I don't have any valley and mountain. It's like a slippery mountain forever. Now, cost is linear. Cost is a scalar. Do you agree? Cost is a scalar. So in this case, my space is 2D. My cost, if you consider the cost as the third dimension, then it's exactly like you are going up a slope, but a linear slope, right? A linear slope. And as you must be in the feasibility set, the solution must be on one of the corners, right? Now, assume you are one of the designers of the simplex algorithm. You want to design some algorithm for solving this linear program. Can you tell me what we should do? We know that the solution must be one of the corners, okay? Start from one corner, that's good. Thank you. You also wanted to say something? No? Okay. Okay, so thank you. So we start from one of the corners, and we know that one of the corners is the solution. So let's go from one corner to another corner. But how do I go from one corner to another corner? I move from one corner to another corner if my cost is decreased. That's one thing. Another thing, I don't jump. I move along the edges. So for example, this is my feasibility set. I start from here. I either go here or here. I don't jump here, right? So I move along the edges, along the hyperplane. Then, for example, from here to here, then from here to here, you see that it's an iterative algorithm until I converge to the best corner where I can't move further. If I move further to another adjacent corner, my cost gets worse. That's the solution. You see what a beautiful algorithm that is. That's called simplex algorithm. Okay, it's a very basic classical optimization algorithm. This lecture is nothing related to simplex algorithm. Why did I say that? Why did I explain the simplex algorithm? For you not to confuse these two algorithms. Okay, now let's go back to our Nelder-Mead simplex method. But why do they call it Nelder-Mead simplex method while it is different from the simplex algorithm? Because this also uses simplex method. Okay, how does it do that? It's so, consider this case. If the dimensionality of optimization variable is d, okay, do we choose d plus 1 random points in the feasibility set, okay, to make a simplex. So simplex, as I said, for example, in 2D, it's like a triangle. In 3D, it's like a pyramid. Now in 2D, for having a simplex, how many points do I need? Can you tell me from this figure? How many points does it have? 3. In 3D, how many points do I need for a simplex? For 4. In other words, by induction, in d-dimensional space, I need d plus 1 points, right? That's why I said, choose d plus 1 random points in the feasibility set to make some simplex, okay? Now, can you guess the idea behind Nelder-Mead simplex method? What? No. So here, note that here my cost is not necessarily linear. It's not just for linear program. What I said for simplex algorithm was in parentheses. It's not related to this lecture. Why did I say that? For you to know what simplex method is, not to confuse it with this one, okay? Simplex algorithm is for linear programming. Nelder-Mead simplex algorithm is for general optimization, right? Okay, so the cost might go down and up. Now the idea is this, it's very interesting. Assume you have some landscape. On this landscape, you make some simplex, right? Then move this simplex. It's like consider the simplex to be a spider. The spider moves on this landscape until it goes down and down the valleys. So when you move the vertices of this simplex, gradually you move it toward the valleys. Do you see? You don't understand? You will see you will see how it is working. But we are moving the vertices. Okay, that's very interesting. How do we move the vertices? We can. Do you agree that we can measure the fitness or the cost value at every vertex? So we know which vertex is better than the other one, right? Yes. No, particle swarm optimization has some particles, and the particles move toward each other with some update algorithm that update formula that we have. Here we are not going to use that update formula. It's updating is more complicated in another way. I'll talk about it. Okay. So now update the simplex iteratively until it converges to the optimal solution. Can you tell me when I'm closer to the solution, my simplex becomes a smaller or larger? Smaller to almost converge to the solution. So my vertices should be close to the solution. In other words, initially my simplex is large for exploration. Gradually, I move toward the valleys by moving the vertices. Also, at the same time, my simplex is getting smaller and smaller. Right? It's getting smaller and smaller until all of them almost converge to the optimal solution. Interesting. So, the initial simplex. How do we make the initial simplex? If the dimensionality of optimization variable is d, choose d plus 1 random points, as I said, to make some simplex. This initial simplex is important. A too small simplex may get stuck in local optimum, cannot do enough exploration. For having exploration, my initial simplex shouldn't be too small, right? It is suggested in paper 1, I think it's the original paper of Nelder-Mead simplex method, to select the initial simplex as the following. So the authors say, select a random point for x1. So because I have x1 until xd plus 1 are the corners of the simplex, right? I have d plus 1 corner, right? Do you remember? So like here, in 3D, I need 4 corners. In 2D, I need 3 corners. So I have d plus 1 corners. For the first corner, let it be random. Then for the second to d plus 1th corner, they are a fixed step along each dimension in turn. So what do I mean? x11 plus some delta. And the rest of the dimensions are the same as the dimensions of x1. Right? Then x3 becomes x12 plus delta. The rest of the dimensions are the same. xd plus 1 is x1d, the last dimension, plus some delta. Delta is some positive, for example, number. And which is not too small. If delta is too small, the simplex becomes too small. Do you agree? Okay. So this is how they have suggested. Okay. In other words, if this is the first point, for example, in 3D, what does it mean? One of the corners will be like here. One of the corners will be like here. One of them will be like here, where these are delta. Did you understand? Okay. In 2D, this is x. One of the corners will be here. One of the corners will be here. Sorry. I apologize. So one of them will be here. So one of them will be along x-axis, the other one along y-axis, right? Okay. Now order. So I'm explaining the stages of the algorithm. We want to minimize the function f. Okay. In the feasibility set, we make some simplex and change it in the feasibility set iteratively to converge to the solution. Okay. So we make some simplex and we change it iteratively. So it's an iterative algorithm. Order. At the start of every iteration, because we have several iterations, at the start of every iteration, we order or sort the corners of the simplex, fx1 to fxd plus 1. We assume that x1 has the lowest cost, then x2, then xd plus 1 until the xd plus. So we sort them as in ascending order, where x1 is the best corner, xd plus 1 is the worst corner in terms of cost. Did you understand? And every iteration, x1 might be different, right? This point, this corner might be x1 in this iteration. In the next iteration, the same corner, which has moved, probably might become xd plus 1, right? So the orders might change in each iteration. But x1 is the best in every iteration. Now centroid. The centroid of all points except xd plus 1 is this. We denote centroid as x by xo, which is what? The mean of all of the points except the worst point. All of the corners except the worst corner. Okay? So the mean of all corners excluding the worst corner. Reflection. The reflected point is defined as this. XR, standing for reflected, okay, is XO. By the way, each X is d-dimensional, right? XR is XO plus alpha. Alpha is some greater than 0 scalar. Usually it is 1. Times XO minus XD plus 1. I'm going to explain to you why. Okay. So consider this figure. Assume we are in 2D. So the D is 2. And these lines are showing the cost values. So along every line, which might be curvy, the cost value is the same. Can you tell me what this cost means that I have drawn here? It's like a bowl going up or down. Do you understand? Good. I think here I meant it's going up. It's like a bowl, but this bowl is not like a sphere bowl. It's like an oval bowl. Okay. Now it's like this. So I have x1, x2, x3. Assume my simplex is this. Which one is the best? Of course, this x1. That's why I named it x1. Then x2, then x3. Agree? Okay. What is xo? The mean of this, which the centroid xo is the mean of all corners excluding the worst corner. So the mean of x1 and x2, right? Agree? The mean of x1 and x2 is here exactly. That's why I put it xo here. Agree? Now, what is xr? xr is xo from here, this point, xo. What is xo minus xd plus 1 in this formula? Xo minus xd plus 1 is the vector connecting xd plus 1 to xo. Agree? So what is xd plus 1 here? x3. x3 to xo. So this is the vector that I just drew. This is the vector xo minus xd plus 1, right? But here I'm saying that add this vector to xo. So starting from xo, which is here, add this vector. Agree? And then I will get xr. But how much do I go in this direction? So because this is a direction, right? How much do I go in this direction? By alpha. So this length times alpha. Why do I usually set? So can alpha be negative? What happens if alpha is negative? So the opposite direction, right? The opposite direction. So what do I mean? So if this is the direction, the opposite direction, because minus times some direction becomes the opposite direction. Becomes like this. Rather than going to the outside of the triangle, we go inside the triangle, or we might go to the other side of the triangle, depending on amount of alpha. Agree? But I want to reflect x3. I want to reflect the worst point. Why am I supposed to reflect the worst point? Because this is the worst. The worst point needs to be reflected. Probably the other side is better. Agree? So let me clean this part again. So here I'm saying that go in from here in this direction, and usually alpha is 1 because I want XR to be exactly the reflection of X with D plus 1. Agree? If alpha is 1, then this length is the same as this length. Right? Okay. So now I think you understand why it's called reflected. So now we can, now that we calculated XR, let's see its cost value. So we have fx1, we have fxd, right? X1 is the best corner, xd is 1 to the last worst corner, xr is the reflected corner, and f of them is the cost of them, right? Several cases might happen. If the cost of xr is between x1 and xd, in other words, if x1 is worse than x, if a reflected point is worse than x1 but better than xd, so it's kind of a middle case scenario, right? Then what happens? Replace the worst point, which is xd plus 1, with the reflected point. So xd plus 1 is set to xr. In other words, reflect this simplex like this, exactly like this. So xr becomes x3 here, and the simplex, which was like this, became like this. It was reflected, right? And go to the next iteration and order the points again. Okay? It has some connection with opposition learning. So the idea is it has some connection with opposition learning, proposed in 2005 and used in materialistic optimization in 2008. What is opposition learning? It's some concept in materialistic optimization, also used in machine learning sometimes, that says that whatever you, for example, in materialistic search, whenever you search something, search is opposite to. Probably that's also good. Or in machine learning, whenever you learn something, learn its opposite to. By the way, it was proposed by Professor Hamid Tishoush, who used to be a professor in systems design engineering, but he went to US recently. Okay, so that's related to that too a bit. Now expansion. Another case, xr might be, f of xr might be less than f of x1. What do I mean? So one case was this. X1, x reflected point was worse than x1 and better than xd. The other case is that xr is even better than x1, better than all of the corners. Then in this case, I define expanded point denoted by xo, which is x denoted by xe, standing for expansion, which is xo plus gamma xr minus xo. Gamma is also a scalar, greater than 1, usually is 2. So let's analyze this formula. So what is this? This is a vector connecting xo to xr. Connecting, so xo is here, right? What is xr is here. So this vector is xr minus xo. But starting from xo, which is here, so I have this direction, I multiply this length by gamma, and I go in this direction. Now, can you tell me if gamma is 1, xe becomes exactly xr? Do you agree? If gamma is less than 1, I will end up with somewhere between xo and xr. But I want to usually go further. I want to go further. As a result, my gamma must be greater than 1, right? So I want to go further than reflected point, right? So I get this xe. Can you tell me why do I want to go further? Yeah. Yes, but that almost answered my question. So xr, we saw that is very good, right? Even better than x1. So apparently, so because we know that xd plus 1 was the other part, was worse. xr is good, very good. Let's go further in this direction. So xd plus 1 bad, xr was good, let's go further, right? Let's expand it. Usually gamma is 2, so we double this length, right? If now we calculated the expanded point, again, several cases happen for the expanded point. We have sub cases in this algorithm. So if the expanded point is better than the reflected point, what does it mean? Apparently this direction is very good. XR was good. XO is even better than XR. Let's go. So we should exaggerate going in this direction, right? Apparently we have found the value. In this case, replace the worst corner with expanded corner, right? However, if expanded corner is worse than the reflected corner, what does it mean? Reflected corner was very good, but when we went further, expanded got worse. Apparently, it was a valley, but suddenly it goes up again, right? In this case, as a result, rationality says that we should replace the worst corner with XR reflected points, not the expanded point, right? And then go to the next iteration and order the points again. This is an example. So here was the expanded centroid. This is reflected point. This is expanded point, right? Now we see the costs. In this case, for example, XE was better than XR. So I replaced X3, which was the worst corner, with XE. As you see, it reflects the simplex, and also at the same time, it expands that, right? But what if XR was better than XE? In this case, replace X3, XD plus 1 with XR, not XE. In this case, we are reflecting that simplex, but not expanding that. Okay? Now, the third case. So one case was that, let's go back. One case was this. X reflected point was between X1 and XD in terms of cost. The second case was reflected point was even better than X1, which was this. The third case now is that XR reflected point is worse than XD. Worse than XD. Again, two sub cases might happen. We still have XD plus 1. So XR is worse than XD, but is it worse than XD plus 1 or not? Okay. If reflected point is better than XD plus 1, in other words, if it is worse than XD, but better than XD plus 1, right? So between these two corners in terms of cost. Then we define something named contracted point. XC, standing for contracted. So XC is this. XO plus rho XR minus XO. Let's see what it means. What is XR minus XO? The vector connecting XO to XR. So XO is here, XR is here, right? These 2 points. So this is this direction, but rho is a scalar between 0 and half. Why? Because I want to go in this direction, but somewhere between XO and XR, right? That's why it's called contraction. Expansion goes further than the reflected point. Contraction doesn't go further than the reflected point. It comes between the centroid and the expanded, the reflected point, okay? And hence the name contracted. So usually rho is half, because I want to be between, exactly between, usually, between XO and XR. I define it as XC, contracted point. Now, we know we have XC, we calculate its fit or its cost. Several cases happen. If the cost of XC is better than XR, if XC, the contracted point, which is here, is better here, it is here, better than XR, what does it mean? So we know that according to this, XR was worse than XD, according to these two, was worse than XD, but better than XD plus 1. In this, in our example, it's worse than X2, better than X3, So it's still worth going in that direction, probably. Okay. But we know that as it is not too much good, so this is not too much good because it's still worse than x2, right? Therefore, we don't go further. We contract it here, and now we calculate its cost and compare it with XR. If X is better than XR, can you imagine what is it? Kind of, I have a valley here, right? Because XC is better than XR. So what does the rationality say? What does the rationality say? It says that replace the worst corner with XC. You shouldn't replace the worst corner with XR because XR is worse than XC, right? Now, what if XC, the contracted point, is worse than XR? What does it mean? So basically, it's like this, right? XC is better than XR is better than XC. So what does the rationality say? Should I replace my X3 with XR? No. In this case, no. They don't do that. But why? Can you tell me? Because XR is not perfect, according to these two. Because of this, XR is still worse than XD. Although it's better than XD plus 1, but it's worse than XD. So it's not worth replacing XD plus 1 with XR in this case. In this case, let's shrink the simplex. Let's shrink it. Okay, shrinking. Replace all points except the best point, x1, with the reflected point. I will tell you what this formula does. So xi, I is from 2 to d plus 1. So I is not 1, okay? Is x1 plus sigma xi minus x1. So let's analyze it. What is xi minus x1? The vector connecting x1 to xi. Xi is one of the corners, which is not x1, right? So consider an example like this. Consider x2 and x1. Assume I is 2 here, okay? So x2 minus x1, the vector connecting x1 to x2 is this, right? Agree? I say x1, starting from x1, go in this direction, but with the scale of sigma, and sigma is half. What does it mean? I will end up here, right? Exactly between x1 and x2. Agree? So basically, this formula is saying that move all of the corners toward x1 with the length of half. So you halve the simplex while the x1 has not moved. One of the corners is not moved. All of the other corners move toward the best corner. x1 is the best corner which is not moved, right? Why should you move the best corner? Don't touch it. It's good, okay? As a result, we are shrinking. We are shrinking the simplex. Then go to the next iteration and order the points again. Do you see the beauty? You see? So here, for example, in this figure, this case has happened where xc was better, xc was better than xr, so I replaced x3 with xc. So in other words, it reflected the simplex. At the same time, it contracted the simplex. But in this case, is this figure. I just shrink I don't reflect the simplex, and I shrink it. Right? Now another case. I know there are cases into cases. You need to concentrate not to be confused. Okay? So do you remember? Still, we are in this case where xr is worse than xt, but now we change this subcase. Now this time, xr is even worse than xt plus 1. In other words, according to these two, reflected point is worse than all of the corners, okay? Including the worst corner. So in this case, we say that the contracted point, we define it to be inside. By the way, the contracted point of previous slide was outside. So we have two variants of contracted points. Contracted point outside the simplex and the contracted point inside the simplex. Do you remember this contracted point of the previous slide was outside of the simplex? But this time, our contracted point will be inside the simplex, like this. Let's see why this happens. What is this? Xd plus 1 minus xo. It's a vector connecting xo to xd plus 1. So this is xo, this is xd plus 1, x3. The vector is this, right? Starting from xo, go in that direction with the scale of rho. And rho is between 0 and half, usually half. So in other words, we go inside the contracted point will be inside the simplex. Can rho be greater than 1? Can it be greater than 1? What happens if rho is greater than 1? I go here. I go here. I will not end up inside the simplex, right? So as a result, rho must be, for example, between 0 and half, or between, right? Okay. Now, again, we have the contracted point inside the simplex. We calculate its cost and see how it compare it with the cost of the worst point corner. If contracted point is better than the worst corner, what happens? The rationality, what does it mean here in this figure? The worst corner is x3, contracted point is here. I'm saying that xc is better than the worst corner, something like this. So it's like something like this, some value like this, right? What does the rationality say? Replace the worst corner with xc, right? Because xc is better than x3. Replace x3 with xc. So it's exactly this figure. So in other words, I have contracted the simplex in the same direction. I haven't reflected that. Okay. Now, what if xc is still worse than xd plus 1? Here, xc. So we know that xr, in this case, was worse than x3. xc inside the simplex is still also worse than x3. So it says that don't replace x3 with anything, not worth it. Shrink the simplex again. Again, we use that shrinking as before, without any reflection. Okay? Then go to the next iteration and order the points again. Okay. So this is the summary algorithm. The algorithm is too large that it doesn't fit in one slide. Okay? So let's see. Well, it's simple. It has just some cases, and it's a rational algorithm. You can understand what's going on. So initialize the simplex with d plus 1 points in the feasibility set. I told you why. Because in 2D, for the simplex, I need 3 points. In 3D, and for the simplex, I need 4 points. In d dimensions, I need d plus 1 points. And then loop until convergence. Any convergence criteria that you want to use, such as maximum number of iterations. Then calculate the centroid. So by the way, initialize, we have initialized the simplex. So I know the corners and I have ordered them. X1 to xd plus 1. X1 is the best and xd plus 1 is the worst. Then calculate the centroid xo, right? Then also calculate the reflected point xr, according to the things that we talked about, the formulas. Now we compare the cost of reflected point with x1 and xd. x1 is the best corner, xd is the one to the last worst corner, right? If xr is worse than x1 but better than xd, replace the worst corner with xr and continue. What does it mean? Go to the next. So go to the next iteration. I mean that. Okay. go to this, go here again. Then else if f of xr, if xr is better than x1, then what happens? XR is very good. It's a hero, better than all of the corners. Then calculate the expanded point, XE. Now calculate its cost and compare it with XR. If expanded point is better than XR, then replace the worst corner with expanded point, right? Because XR was a hero, XE is more hero or heroer. I don't know what this, more hero than the reflected point. XR was good, XE is better even. So replace XE plus 1 with XE. Otherwise, if XE is worse than XR, so XR was very good, but XE is worse than XR, it means that we shouldn't exaggerate going in that direction. So replace XD plus 1 with XR, reflected point, not the expanded point. Okay? And then continue to the next iteration. The third case, so do you see? These are the main cases. Case 1, case 2, case 3. Because XR is either between X1 and XD, or better than X1, or worse than XD, right? 3 cases. So if XR is worse than XD, then again 2 subcases happen. Is it better than XD plus 1 or worse than XD plus 1? If XR is better than XD plus 1, calculate XC contracted point, I think outside of the simplex, if I'm not wrong. Okay? Then see if the contracted point outside the simplex is better than the reflected point, replace the worst corner with the contracted point outside of the simplex, right? In other words, you reflect the simplex and also at the same time you contract it. Otherwise, if XC is worse than XR, we are in this else, what does it do? Shrink the whole simplex without reflection. Now in this else, it means that XR is worse than XD plus 1. So in other words, XR is worse than all of the corners. Then calculate the contracted point inside the simplex. Then calculate its cost. If its cost is less than XD plus 1, so what does it mean? If XC, the contracted point inside the simplex, is better than the worst corner, replace the worst corner with the contracted point inside the simplex according to rationality. Otherwise, it's not worth it. Just shrink the simplex without reflection, right? It's just a bunch of if-elses, right? Any question so far? No? So another YouTube video of mine about this algorithm is this. Feel free to watch that. I have in that YouTube video, I also have explained simplex, Nelder-Mead simplex method. And these are the references. Let's see. I think there is a good GIF about the Nelder-Mead simplex method. As far as I remember, there was a GIF. Yeah, here it is. Wikipedia. Thank you. See? Do you see different operations that we talked about? Shrinkage, reflection, moving. So you can see the simplex as a spider moving on the landscape. And this spider tends to move toward the valleys. And while it is moving toward the valleys, it gets smaller and smaller. Yes.
Is it possible to do this for like null greater than 10?
What do you mean?
Like, you need to know the variables ahead of time to do it.
The variables?
Yeah, like why don't you train models?
So these do you remember we said when we have an optimization problem, we have two broad paths to solve this optimization problem, either classical optimization or search, materialistic search. And in some cases, we have to do materialistic search, such as when it is too complicated, when it is highly nonlinear or highly non-convex, when you have too many constraints, or when it is, especially when it is black box. When it is, do you agree that I can use Nelder-Mead simplex method even if the cost function is a black box? This is visualization. You know in the visualization how the cost is. Assume I have no idea how the cost is. I have just black box. Assume I want to do reverse engineering. I have black box. Then I can, the only thing that I can do is that I give inputs to this black box, it gives me outputs, corresponding outputs. When the function is a black box, you cannot calculate gradient. The whole classical optimization goes down, right? So as you see, materialistic optimization usually, I think 99% of them only use cost evaluation or fitness evaluation. They don't use gradient mostly, right? But if you can calculate gradient, why do you do search? Because classical optimization guarantees you, has guarantees, theoretical guarantees. Why do you want to do search? When you can do it in a more solid way, why do you do search? Right? Exactly like saying that when you have the ability to do something, why do you use tools to do that? Right? Just do that. Use the classical optimization algorithms which are strong, and deep learning is very strong. Gradient descent is very strong. You understand? Does it answer your question?
Yeah.
Okay. Any other question? Yeah.
Theoretical guarantees.
Yeah.
What does the Nelder-Mead have theoretical guarantees so that you caught it?
I think, as far as I know, it might be because of lack of my knowledge, but as far as I know, they don't have any theoretical guarantee. Materialistic algorithms mostly don't have any theoretical guarantee, and that's why when you go to optimization department, they hate these parts. If you talk about these algorithms with a professor in mathematics or department of combinatorics or optimization, they will go away without even answering you. Okay. They don't like this. They like mathematics. Okay. But they are working very well. That's why it's been used in MATLAB. Okay. Mostly they are used in engineering problems. And we are here in the engineering department, right? Okay. Any other question? No. I myself remember I passed an optimization course, and the professor said in that course that I don't like materialistic optimization at all. He himself said that. But it doesn't mean that it's not useful. I think we have seen how useful these algorithms are, right? Let's have a break and come back at 5 to 9. 5 to 8, sorry. So 5 to 8, right? 5 to 8, and we will continue the session. So materialistic optimization is over. Now we go to the next part of the course, which is game theory. Okay, yeah, interesting. Okay, so before we continue the session, some people ask me about how to write a report and this is. So by the way, your project, try to add something to the wall. I think you understand what it means, right? Don't just replicate the previous things. I think replicating is fine as a project when you were in high school, right? We are in undergrad here. at the last year of undergrad, so we should add something to them. That's one thing. And also follow your passion. Don't force yourself. See what passion all of your teammates are looking for and go ahead with that. And also do comparison and analysis. So compare with the benchmarks, different baseline methods. An example is that if you want to do, for example, ant colony on a graph for finding shortest path, you can also compare it with baseline methods such as Dijkstra, right? And these things. And also your report. Do you know how we should write a paper? If you don't know, that's so simple. Don't worry. One of the simplest things in the world. So you start. By the way, do you know LaTeX? I think you can learn LaTeX in half an hour. Okay, just YouTube it, tutorial LaTeX, and put it on the speed 2. And it will give you the whole thing. I think speed 2 you can watch an hour tutorial in half an hour and give you it will give you all of the details. So basically in LaTeX you should know how to write equations, inline equations and outline equations, whatever you call it, and how to refer to the equations and sections, and that's it. And the rest is like Microsoft Word. Okay, but LaTeX is very beautiful. I suggest that you write it in LaTeX, but I don't force it. So I will give you the templates of the IEEE conference paper, which has both LaTeX and Word. Choose whichever you want. But I think it's a good practice for you to try LaTeX. And also, so writing a paper is one of the easiest things in the world. How do you do that? You write abstract, and then you write usually maybe keywords, and then introduction. In introduction, you introduce your problem and maybe related work. So in introduction, you also have related work and cite them. And then at the end of the introduction, usually introduce your sections. In section this, we did do this. In section this, we do that. And then we start the methodology section. Some people break down this methodology section into several sections, right? With different names. You can also have subsections. So you can break down your section into subsections. You can also have subsections, right? But don't go further. And then you explain your methodology, and then you go to simulation part. Some people call it simulations. Some people call it experimental results. Some people call it experiments, depending on where which field you are working in. I have heard that in embedded systems, maybe related to mechanical engineering, when they say experiments, apparently they mean something real world, right? When you experimented on real world, for example, you are designing a table, you actually design the table and show it its tolerance to heat and different things. This is called experiment for embedded systems for mechanical engineering. And simulations means whatever you do in computer. But in machine learning, they call everything in computer either simulation or experiments. They don't care much about this distinction. So then in an experimental section, you usually introduce your data set or data sets, benchmarks, and you show your results, and also you compare. You show your comparison to the other methods, or try to show your results in a way that it convinces the reader that it is working. Also try different plots. Try different plots, visualizations, tables, and show different comparisons and analyze the results and also analyze the comparisons. Don't show, okay, this is the result. But this is the result, what? Say that this is working better because of this, this is this. Try to analyze the results. And at the end, you have usually conclusion and future work. Some people, that's funny, a joke, that if you don't write any future work in your conclusion section, it's completely redundant. because they usually make the abstract and they change all of the verbs to past verbs, and it becomes a conclusion. But it's, I think, redundant. So try to include some future work or future directions in your last section, not to be redundant. Otherwise, it's just abstract with past verbs. And yeah, and then afterwards, references come. Any question? Yes.
Is that for the project or for the exam?
This one that I just explained for the project. And now, can you judge whether was it easy or hard? Well, one of the easiest things in the world, right? Right. And who says that you should start from start to bottom? The order is yours. You choose in which order to write the paper. This was the organization of paper, but you might not start by writing methodology and then experiments and then go to introduction. So it depends on how you want to write it down. I think the easiest part to write down is the methodology, because you know your method very well. The hardest part is usually introduction. Although it might seem easy, but it's hard. Okay. Just let me tell you in parentheses some hack. I think that these hacks are more important than the main course. When you want to write a paper, get published, okay? Listen to me, because this is important for you if you want to go to master's or PhD. When you want to write a paper and publish it, you need to compare it with baselines, right? What if you compare it and see that it's not working well much? At least it is working well, better than some methods, but one of the methods is very hard. If it is one of the methods, that's fine. Include it in the results, and the reviewers understand that, because they know that there is no perfect algorithm, right? Also, if you always say that you are the best, if you get if you have too much ego, they will reject you probably. So be humble, but try to be better in most cases. If in some cases you are worse and you don't want to report that, but you have to cite it because it's related. So you bring it to the related work and cite it wisely. When I say wisely, what do I mean? Cite it in a way that the reviewer doesn't ask you later, why didn't you compare it? Okay. The more you write papers, the more you understand these hacks. By the way, another hack. You want to do something, and you know it's a pain in the neck, it's hard to do it. You put it in the future work. Okay? You put it in the future work, but why do I say that? Why should you say that in the future work? Because it will block the review of the review of the reviewer. If the reviewer says, why didn't you do that? You will say, I have left it to future work. Do you understand what I'm saying? These are the hacks. Try to. Yeah, you will learn these when you write papers. Okay. Any question? No? Okay, let's start the second part of the course, and that's game theory. That's very cool. Okay, introduction and game elements. Elements of a game. Okay, game theory. So actions of decision makers. So we have some decision makers which make decisions, and we have some actions done by them. Actions of decision makers who are conscious that their actions affect each other. When we say, I know that whatever I do will affect the other person or the situation. When they are conscious that their actions affect each other, then these actions are called game theory. Okay, we have some players or agents or decision makers, whatever we call it. The individuals who make decisions, right? Those are called players or agents. For example, in reinforcement learning, because there is connection between reinforcement learning, multi-agent reinforcement learning, and game theory. They call them the players' agents, right? Action, a choice made by a player the player has some actions to do, right? A choice made by a player. Payoff or utility. So two names for the same thing. The utility or benefit received by a player either at the end of the game or in expectation before playing the game. So every player has some benefits, right? For doing something. Otherwise, why do they do that? They have some benefit for playing the game. Then, so we usually, sometimes we take the benefit at the end of the game, or we take it in the expected value. Okay. This is called payoff or utility. Can you tell me, do we want to increase our payoff or decrease it? Want to maximize it or minimize? Maximize, right? I want to maximize my benefit, my utility, my payoff, right? Information. The amount of information that every player has about the game. Okay, amount of information that, because not everyone knows everything, right? Not everyone knows everything. We know some subset of the information available to us. And strategy. The plan a player uses to maximize its payoff. By the way, I use its not to get complicated with his, her, whatever, there. It, okay? The plan a player uses to maximize its payoff. Okay? So a player wants to maximize its payoff, and the strategy is the plan to do that. It is a subset of possible actions taken but depending on the information available. So what do I mean? Every player has some information. Depending on the information and the situation, it will choose one of the available actions. So every player has some available actions, right? It will choose one of the actions and goes with that. So which action to choose? That's called the strategy, right? The strategy of the ith player is denoted by SI. SI, S standing for strategy. I for the ith player, right? The payoff of the ith player is denoted by pi I, S1 to Sn. So pi I is standing for payoff. Pi I. Payoff of the ith player, okay? Payoff of the ith player, and S1 to Sn are the strategies of first player to nth player. By the way, the number of the players is denoted by n. Oh, okay. Now, can you tell me why is pi I a function of S1 to Sn? Yes. Exactly. Whatever other players do, also whatever I do. So including whatever I do and whatever other players do will impact my total payoff at the end, right? Of course, if it is if the players are enemy, I want to increase my payoff. The other players want to decrease my payoff. They want to increase their own payoff, right? If we are enemies. Okay, n is the number of players. This means that based on the chosen strategies of the players, the payoff of every player is determined, right? Okay. Now equilibrium. Equilibrium. The set of all selected strategies selected by each player is known as the equilibrium. So in every game, every player chooses some strategies, right? The set of all selected strategies which the players have chosen for that game is called equilibrium. Basically, you can see equilibrium as kind of convergence, right? Where does the game converge? We call it usually in the game theory is called equilibrium. Okay. Outcome. By the way, when I say the game doesn't have any equilibrium, what does it mean? It never settles down, right? I do something, then assume it is two-player game. I do something, then you do something, then it's not good for me. I do something, then it's not good for you, you do something. It's not good for me, I do something. It never ends, never settles down. It means that there is no equilibrium. But if after several interactions, I'm fine with the result, you are fine with the result, all of the players are fine with the results, it's called equilibrium, convergence. We have settled down, right? Outcome. The equilibrium strategies dictate the outcome of the game. So what is the result of the game, right? What happens? For example, I do this, I do that, you do that, and what happens? This is outcome. Depending on the game, games might have different outcomes. Nature. Nature is an important element of the game. It's a pseudo and non-strategic, pseudo and non-strategic player, I'll tell you what these mean, whose actions are taken purely mechanically. So nature is a pseudo player. You can see it kind of as one of the players, but it's not one of the actual players. So for example, it's considered a two-player game. I do something, you do something, but something might happen randomly, right? This is called nature. And the nature, usually its actions are taken randomly, but with known probabilities. So we know the probability distribution of the nature, but it adds some randomness to our game, okay? And as you can guess, the nature determines the situation of the game. Consider a duopoly, for example. Two big companies wanting dominating the market, doing something, and whether there is a recession or not. For example, there might be a recession with some probability, right? Whether the recession happens or not is called nature. Right? And you know that when we are in a recession, the players will act differently. If there is no recession, the players will have other behavior, right? So the situation of the game changes by the actions of the nature. And this is stochastic. By stochastic, I mean it is random, right? And as you see, it's pseudo player. You don't definitely say it's a player, one of the players, but it has effect, right? And it is non-strategic, so it doesn't care what players do, right? Doesn't care. So that's why it's a non-strategic. Strategic players are the rational players which see what others are doing, so I do this. But nature doesn't do that, right? Nature, recession happens or not, it doesn't ask, did you do this or didn't you do that? So taking random actions at specific points in the game with known probabilities. Each action by nature leads to different realizations or possibilities or situations of the game. Any question? No? Okay. Action set. The set of all possible actions for a player, denoted by AI, where a small AI is what? One of the actions of the ith player. Capital AI here means the set of possible actions. Every player has a set of possible actions, right? And they do not necessarily have the same set of actions, right? My actions might be enter the market or exit the market. Your action might be increasing the prices or decreasing the prices, right? The actions might be different for the ith player, or they might be the same. Maybe we have two players, both with the actions entering market or exiting the market. Okay. Action profile. A list of all actions taken by all players, denoted by A. So A, what does this notation mean? Is defined as actions AI, where I goes from 1 to n. Right? So the actions of the players in the game, if you consider them all together, it's called action profile. Right? By the way, this is wrong, sorry. Okay. Cooperative game. So now in this slide, I'm gonna talk about cooperative game versus non-cooperative game. Okay. So a cooperative game, a game in which the players can cooperate and make binding commitments. So basically, if in a game, the players can collaborate or cooperate with each other, then it's a cooperative game. By the way, cooperative game doesn't necessarily mean that the players don't have any conflict, right? We might have some conflicts, but we cooperate. Or we might not. So I'm saying that when we might have conflict and cooperate, we might not have conflict and cooperate. If we don't have any conflict and we still cooperate, what does it mean? Our payoffs are along each other. If we have conflict, but we are cooperating, it means that our payoffs are not necessarily along each other exactly, but we still cooperate with each other, right? Non-cooperative game is the other way around. Is where in a game where the players cannot make binding commitments. So they don't cooperate with each other. They don't collaborate with each other. Again, they might have conflict. They might not have conflict, right? Although they are not cooperating. In the non-cooperative games, the players are usually selfish because they don't want to cooperate. Or selfish. They only think about themselves. They want to maximize their own payoff only, and they don't care about others, right? 4 cases may exist: cooperative game without conflict, cooperative game with conflict, non-cooperative game with conflict, non-cooperative game without conflict. So let's see the first case. Cooperative game without conflict. They collaborate to gain mutually. Can you give me some examples, real world examples? Cartel, can you explain more?
Like drug dealers come together and then they say we're all going to set our prices this.
That's
we all make money.
exactly. That's so a cartel of drug dealers, and they say let's reduce the price of the drug or increase it. I don't know, right? So they collaborate with each other and their payoffs are along each other, right? Another example is OPEC, right? Setting the price of the oil, for example, right? Because when they increase the price of the oil, all of the countries in the OPEC will have benefit, right? Another game is cooperative game with conflict. I have given you an example here, such as bargaining over price. So we go to a shop, you are the owner of the shop, you want to sell something, I want to buy something, right? We are cooperating with each other. I say, please decrease it. You say, no, this is too low. I say, okay, not my word, not your word, something in between, right? So we bargain with each other until we have some equilibrium, some convergence, which is usually higher than what I suggested and lower than what their selling price, right? So this is, can you give me some other examples? So we cooperate with each other, but we have conflict.
Survival game.
Survival game, can you explain what that is?
Water, but since it's limited, you're more selfish.
Okay, so I think Hunger Games you mean. Yeah, so that's a great example. Thank you. Let me add it to the slide. So, or Hunger Games. Have you seen its movie? If you haven't seen that, it's very interesting. Hunger Games is one example. I just found another example. What was that Korean series? Squid Games, right? Squid. How was it spelled? I forgot. Squid? Was it right? I don't know. I don't remember how it was spelled. Squid Games. It was very famous series. So if you haven't, Hunger Games was a movie, a series of movies, saying that they had to kill each other gradually, but some people collaborated with each other to kill some others, but they knew that eventually they have to kill each other. So they made teams to kill some other teams, but the people inside the same team are cooperating, although they have conflicts, right? What? Because the rule of the game was that only one alive person should come out. That was Hunger Games. I think these are just examples of real world as well. These are just metaphors. Okay. Squid Games is another game, is another movie series, I can say, that they were playing, and they had to pass some games where they had to survive, otherwise they would die. So losing was equivalent to dying. But I think in one of their games, we actually saw that a cooperative game with conflicts, kind of. For example, the game where they had to throw their balls, their small balls. Whoever throws further will be alive, but the other person who doesn't throw it far enough, they will die. At some point, some people sacrifice themselves so the other person stays alive, right? So that they were cooperating with each other, but although they had conflict, one of them would be alive and the other one would die, right? Another example I just found out, it's coming out, the movies are coming in my mind. Have you seen, I think, The Cube? Have you seen the movie The Cube? Is it called The Cube? Oh my God, it's a good metaphor for the world. So it's like a big building, people sleep, and they wake up and they see themselves in some floor in the building. Every floor has two people, okay? Once a day, some dish of plates comes down the floors, and people eat out of this dish of plates. Of course, you can see that the people who are in the above floors, they are luckier. The platform, sorry, I apologize. The platform. I think The Cube was a horror movie, right? Yeah, The Cube was another, because I like horror movies. So, but the platform, sorry. The Cube was another movie. The platform, so we have a platform of the floors, and plates of a dish of plates comes down gradually. So it stops for 5 minutes at every floor. Can tell me? I think you can guess that the people at the top floor, they are luckier. They eat fresh food and they have a lot of food. But the more it comes down, the less food remains. And after some level of the floors, the people will stay hungry and they will die because of hunger. And it was showing that because of hunger, people used to fight with each other, even in the same floor. And then someone suggested, let everyone eat a little bit, not too much. The people who are in the top floor, they shouldn't eat to become completely full, because this is equivalent to hunger of the below floors. Therefore, they said, let's eat a small portion, so everyone can survive. But the people on the top floors, they were so selfish, right? They were so selfish that sometimes they used to pee on the people in the below floors. And I think you can see that this is a complete metaphor of the world, right? It was a very great movie, in my opinion. And suddenly someone said, someone went on the dish of plates on that with some knife and forced people not to eat too much, so people below the building can eat. Okay, that's a good example. So we have a lot of movies, good movies. If you haven't watched them, put them in your list to watch. Okay, another game is non-cooperative game with conflict. So what does it mean? So we don't collaborate, we don't cooperate, but we have conflict, such as the prisoner's dilemma. I will tell you what it means. We will talk about it, but briefly let me tell you. We have two prisoners. They have done they are guilty, for example, right? But we don't put them in the same room, and we talk to them. We investigate them. Is that correct? We investigate them. So two police officers investigate them separately, and they say they should confess or not. If some of them denies and the other one confesses, it means that that person will be released, but the other person will be in jail, right? So they have conflict, the two prisoners, but they don't cooperate with each other because they can't even see each other. They are in different rooms. Or another thing is that game of chicken. What is game of chicken? Have you heard of it?
Two people are driving towards each other on a one-lane road.
Exactly.
Like, who's gonna steer off?
Exactly. So the game of chicken is that, let me repeat it so to be recorded. So two teenagers or usually there are two young people. They have two cars. They drive their cars toward each other with fast pacing, and whoever steers off first will lose. Of course, if none of them steer off, they will have accident and they will both die, right? So it's kind of saying that who is braver, okay? Although it's crazy, but game of chicken, they are having conflict. Who steers off first, and they are not cooperating with each other. The fourth case is non-cooperative game without conflict. For example, two companies set a product standard without communication. Okay, so they don't cooperate with each other and they don't have any conflicts. Don't have any. Two companies that are not, assume two non-related companies, right? Apple, which makes phones and these things, and another company, I don't know, LG, maybe. They're not that much related, I think. But so they are non-cooperative without conflict. Okay. Okay. Now representation forms of a game. So normal form, there are two important forms of representing games. So normal form and extensive form. When we want to represent a game, there are two main forms to represent them. One of them is normal form, the other one is extensive form. In this slide, I'm gonna introduce normal form. In the normal form, the game is shown as a table or payoff matrix. Okay, like this. You see it? Like a table or payoff matrix. It's like a matrix, where the rows and columns correspond to the actions of the first and second players respectively. So player one, the rows correspond to player one, and columns correspond to player two. But what are the rows and columns? They are actions. You remember the set of possible actions. Player one has some possible actions, so it has several rows. The player two has some possible actions, so we have several columns. Now, can you tell me what if I have more than two players? Becomes a tensor, right? For example, if I have three players, it becomes like a cube, like a matrix, right? Rows, columns, and heights. Do you agree? If I have four players, it becomes a rank 4 tensor. So the normal form can be either for the simultaneous move game and ordered or sequential move games. Let me tell you what these mean. Simultaneous move game means that the players play simultaneously. So when a player, so they don't wait for the other person to move first. I do something at the same time you do that thing. A good example is what? Cross scissors. What is the name of that game? Cross scissors. What was
Rock, paper, scissors.
rock paper scissors? Rock paper scissors. Or the other one is tic tac. Right? Tic tac toe. Tic tac toe. Whatever it's called. So they are played simultaneously. Sorry, tic tac toe is sequential. I apologize. But rock scissors is simultaneous because I don't see what you have brought and then I bring. We do it simultaneously. The other types of game is ordered game or sequential move game. We move sequentially like tic-tac-toe, right? I do something, then you do something, then I do something, right? So the normal form can be used for both. If it is simultaneous move, then the order doesn't matter, right? The order doesn't matter. But can you tell me what if it is sequential move? How do I show the order in the table? I don't show the order in the table. I write it down below the table. Okay? I say these are the payoffs, but the order is this. The order of game is this. Okay? Did you understand? So this is the table, and then I say order of game column. This is I explain it. Okay. But I think you can guess that normal form is usually used for simultaneous move game. It's more suitable for simultaneous move game. Okay. For order games, as I said, the order of players should be mentioned in addition to the table. Some example is this. So new cleaner is player 1, old cleaner player 2. When I say player 1 and player 2, I don't mean that player 1 moves first. I mean two players, player 1 and player 2. Player 1 has, for example, actions enter, stay out. Old cleaner player 2 has actions low price, high price. Can you say what game is this? It's like two companies, okay? Two cleaning companies. One of them is old cleaner company. The other one is new cleaner company. Old cleaner company has been cleaning in market for 3 years. New cleaner company is just entering the market. So can you tell me the actions of the new cleaner is whether to enter the market or stay out? The actions of the old cleaner company is whether to set the prices low or high. I think you understand why, for example, if the new cleaner enters, maybe the old cleaner sets the prices low, so it wins the market again, right? For example, and these are the payoffs. Can you tell me what these payoffs mean? So when I say in every cell, when I say pi 1, comma pi 2, so the first one is the payoff of the player 1, which is in the rows. The second one is a payoff of the player 2, which is in the columns. An example is that if, for example, new cleaner enters and the old cleaner has low price, then the payoff the new cleaner will be minus 100. The payoff the old cleaner will be minus 50. Right? Can you tell me why? Usually games make sense. So it is bad for new cleaner to enter because the old cleaner has dominated the market. Also, if the old cleaner sets the prices low, its reward is negative. Why? Because it is losing some money. What about this one, this cell? The new cleaner enters, the old cleaner sets the prices high. In this case, the payoffs are both 100. Does it make sense? Yes, let's see. The new cleaner has entered, the old cleaner sets the prices high, but because of that, the new cleaner has a chance in the market. Because the prices of the old cleaner is high, so its payoff is 100. But the old cleaner still is benefiting because of not losing the money. Its prices are high, right? What about this cell? The old new cleaner stays out. The old cleaner, low price. Its payoffs are 0 and 50. So new cleaner stays out. Its payoff is 0. Doesn't gain anything. It didn't even start the marketing. Old cleaner, low price, 50. Old cleaner gets something, although it is losing some money, but gets something because it's the monopoly. It's dominating the market still, right? What about this one? I think you understand that why it is 50 rather than 100, because it's still losing money. I think when the new cleaner stays out, the old cleaner has set the prices low, the old cleaner will regret a little bit. But can you tell me, was it rational for old cleaner to set the prices low? Yes, because the old cleaner never knew that whether the new cleaner enters or stays out. When it sets the prices low, and then suddenly says, because it's simultaneous move game, it sees that the other person didn't come in, right? I'm in the market. What about this one? The fourth cell. So new cleaner stays out, old cleaner sets the prices high. 0, 300. 0 for new cleaner because it never enters the market. Old cleaner 300 because it's dominating the market, it's monopoly, and also its prices are high. Yes. Yeah.
For the old cleaners with low price, the options are negative 15. But for high price, it's 100 and 300. Why would they enter those?
Negative 100, or is it
For the old cleaner?
here? For the old cleaner, which cell, sorry, are you talking about? Old cleaner, low price. What about new cleaner? So old cleaner has 2 actions, new cleaner has 2 actions. So we have 4 cases. In each case, we have different payoffs for the 2 players. Okay, now what was your question? Yes, exactly.
The options are 100 and 300.
Yes.
Why would the old cleaner ever stay with a low price?
So, yes, it's the game. I haven't yet explained the equilibrium. If we analyze the equilibrium, some cells don't make sense for the equilibrium. Okay, some cells are making sense for convergence or equilibrium of the game. But here I'm just explaining the payoffs. But we will solve the game. Okay, answers your question. Okay. By the way, here in this example, I have 2 actions per player. If I have more actions, I will have more cells in the table, right? And the table doesn't need to be a square matrix. Maybe one of the players might have more number of actions than the other one. Any question? No? Now the other form, extensive form. In the extensive form, the game is shown as a tree. Okay, it's a tree. A configuration of nodes and branches running without any closed loops. I think it's the definition of tree. It doesn't have any loop. Tree is a graph which doesn't have any loop. Okay. So a configuration of nodes and branches running without any loops, closed loops, from a single starting node to its end nodes. Okay. So it's a tree, an indication of which node belongs to which player. So we say which node belongs to which player, and the probabilities that nature uses to choose different branches as its nodes. So one of the nodes might be nature as a pseudo player. Then also the payoffs for each player at each end node. So at the end nodes, we write down the payoffs. Okay. Usually the order of the payoffs is the same as order of appearance in the tree. So for example, the tree is going like this, right? First, the new cleaner has appeared. So the first payoff is for the new cleaner. Then the old cleaner has appeared. Then the second payoff is for the old cleaner, right? By the way, usually it's like layer wise. So layer 1 is one player. Layer 2 is the other player. Okay. And I think it's obvious that so here it's a binary tree because every player has 2 actions. If every player has 3 actions, it will not be a binary tree, right? Assume the old cleaner has 3 actions, possible actions. New cleaner has 2 actions. Then I will have these 2, but here I will have 3 things, right? Did you understand? And I think now it makes sense to say that, by the way, this is called extensive form. Extensive form can be used for both simultaneous move game and sequential move game or ordered game. Folks, consider that simultaneous move game that I talked about, and you can still represent it as the tree. And these payoffs are like the cells in the normal form, right? The table of the normal form. If it's a simultaneous move game, then I don't care about the orders here. So it's not representing the time flow. But extensive form is very suitable for showing ordered or sequential move game. In this case, then this shows the time flow. So the sooner the player appears, that player has the sooner move, right? Sooner action. For example, if it is a sequential move game, the new cleaner first enters or stays out, and then old cleaner sees its action, sees what the old new cleaner has done, then decides what to do. As you see, when we have sequential move game, the players, or at least one of the players, knows more, has some benefit of knowledge, right? Any question? We also have game tree, which is a bit different from extensive form. Everything is the same as extensive form. One difference, that in a game tree, at the end of the end nodes, rather than payoffs, I have the outcomes. For example, the outcomes can be the actions, or you might define outcome for your game differently. Doesn't matter. When you write outcomes at the end, it's called game tree. But when you write payoffs at the end, it's called extensive form. Okay? Now, let's review some well-known 2-person games. Well-known 2-person games. So what do I mean by 2-person games? I have 2 players in a game. Okay? Some of them are very well-known, very famous. Let's review them. Please focus on this because I think you will enjoy it. Okay. This course, you know that it's only for joy, right? For learning. Enjoy learning. Okay. So there are various games, some of which are more well-known. A game may be explained in an example situation, but it can be used to describe a backbone scenario in various situations. What do I mean? I may tell you, I may introduce to you some game with some specific name, but don't think that this game is restrictive to that situation. You might see that game in your own life. It's just a metaphor. In this section of the course, you are in addition to learning game theory, sometimes you learn how to live, what to do in different situations of your life. Okay? So they describe backbone scenarios in various situations. In other words, we observe and deal with these games in our daily lives. Some of the well-known 2-person games are introduced in the following. They're very famous. Two-person, you have 2 players. First one, Prisoner's Dilemma. So, Prisoner's Dilemma, it was proposed in 1993. So two criminals are under arrest. Okay. Policemen, by the way, it might be useful for you if you get under arrest. Okay. Two criminals are under arrest. Policemen or police officers talk to two prisoners separately in two different rooms, two different investigation rooms. You have seen those rooms, right? With mirrors, and you sit there, and that person usually talks harshly to you. So if a prisoner cooperates, in other words, confesses to be guilty, and the other prisoner defects, in other words, denies being guilty, the cooperating prisoner will be in jail for 3 years, and the other one will be freed. By the way, when I say 3 years, can be any number. Here, this is an example, right? The relative payoffs are important. So when I say 3, when I say the other payoff is 2, 3 must be greater than 2. But you can say rather than 3, you might say 8 years. 8 is still more than 2, right? The relative payoffs are important. So if one of them confesses, the other one denies, the person who cooperated with police will be in jail, the other one will be freed. If both cooperate or confess being guilty, they each are in jail for 1 year. So the police officers will give them some reward. They say, okay, both of you confessed being guilty, so we in jail you only for 1 year, each of you, because the guilt will be divided between them, right? If both defect or deny being guilty, they each are in jail for 2 years. So the police officers say, okay, you don't collaborate with each other, with us, so the case will not be solved at all. Until it is solved, you must be in the jail, right? Assume there is no lawyer and they put you in the jail. So if both deny being guilty, then the case has not been resolved, so they each are in jail for 2 years. The number of years may change in the game, as I said, but the relative relation between them should be preserved. And can you tell me, do you see that there is some conflict here? You see the conflict. The person might think, at least for several seconds, should I confess being guilty or not? You might say, probably in the first glance might say, deny and say, I didn't do anything, let me be free. But how do you know that the other person confesses being guilty? Maybe that other person also says that I'm not guilty, and then you both will be in jail for 2 years, right? So you don't know what to do. So this is again the game. By the way, we will solve this. We'll see how they are, what is their equilibrium. Prisoner 1, prisoner 2. So either cooperate or defect. Cooperate or defect. Okay? If they both cooperate with the police officers, the guilt is a split between them. They both get payoff -1. So 1 year jail for prisoner 1, 1 year jail for prisoner 2. If one of them cooperates, prisoner 1 cooperates, the other one defects, prisoner 1 will be in jail for 3 years, but the prisoner 2 will be freed, 0. I think it's symmetric, right? It's a symmetric game. So it's 0 - 3 also here. What about this case? They both defect. They say we didn't do anything. So the case is not resolved. So they both are in jail for 2 years each. And so not necessarily defecting is good, because what if the other person also defects? But not necessarily cooperating is good, because what if I cooperate and the other person defects, right? It's a hard scenario. And you can see it a lot in your life, not just for prisoners. You see it a lot in your life. You can think of that. I think maybe several days a year you might see this in such cases. Okay, by the way, don't get confused when you see it online. Look it up online, this game. Sometimes in the literature, when they say confess, they mean defect. I don't know why. It's a bit weird. When they say deny, they mean cooperate. But why didn't I use the cooperate, confess and deny in the table? Because of not having this confusion. Cooperate means that they say I'm guilty. Defect means that I'm not guilty. Okay? Okay, don't get confused. So any question? Any question? And as you see, the games are showing the hard scenarios. If there is this scenario, everyone knows what to do, right? The game of chicken. We talked about it briefly, but let's go over that again. The game of chicken, also known as the hawk dove game or snowdrift game. Reference 3. Two teenagers play a game where they drive their cars with fast pace toward each other, right? If one of them swerves or goes off the road and the other one continues driving, the one who continued wins the game because it is braver. If both continue driving until the end, it means that they are both crazy, so they will crash and they will both die because of the accident. If they both swerve, they get off the road, they both lose but will not die. Okay? Now, do you see the hard scenario here? At every time while driving, every player thinks, should I swerve or not? Let me continue further. But it's getting risky. I might die. Should I swerve or not? If I swerve, what if the other person doesn't swerve? Then I will lose. But what if I don't swerve? I might die, right? So, teenager 1, teenager 2, continue or swerve the action. They have the same actions in this game, like before. So if they both continue, they will both die, -3. This is let me finish it. This is the worst payoff for both of them. If one of them continues, the other one swerves, the one who continued will win with payoff 2. The swerves one gets 0. It's still better than -3 because -3 means dying, right? But it's 0. But it's lost the game. It's a symmetric game, so the other way around is also 0 too. But what if they both swerve? They will each get 1 because they were both losers. They weren't brave enough, right? So 2 is better than 1 because 2 means winning, 1 means losing. 1 means that both lost. So both losing is less shameful than only you lose. If only you lose, your payoff is 0. If both of you lose, it's less shameful. So its payoff is 1. But if you die, its payoff is -3. The relative payoffs are important. Okay, your question?
Normally, I think it's the same because like in this case, like dying versus
Yeah, I'm saying that the relative things. You might say dying is -100. You can say -100, -100, 2, 0, 0, 2, 1, 1. Relative. So that's also a game of chicken. That is a game of chicken. This is also a game of chicken with different payoffs. Then I think the more, if you exaggerate on these, they will be more scared, right, of dying. So if it is -3, it means that they are crazy. They don't care if they die much. But if it is -100, it means that they value their lives a lot, right? Any other question? No. So similar scenario. Grab the dollar game. I think I have explained it here. And not a similar scenario to game of chicken is grab the dollar. Grab the dollar game, reference 1. Have you seen it? Of course you have seen it. Can you tell me where have you seen it? Can you guess? Grab the dollar from the name without looking at it. Grab the dollar. The entertainment shows. So I will tell you what it. There was an entertainment TV show named Let's Make a Deal. But we have similar shows like that too. You can Google it. It's an old show. Okay, Let's Make a Deal, where two contestants should decide about some dollar as the result, as the reward. By the way, this is not $1. It's maybe $1,000. Okay, so they should decide about it. Each of them can either grab the dollar or not grab it. So the actions grab or not grab, and they have both the same action profile, action set. Okay, if both grab the dollar, they lose the dollar. Do you see? If they both grab the dollar, they lose the dollar. By the way, it's a simultaneous move game, because if one of them moves, the other one knows what to do. Doesn't make sense. It's a simultaneous move game. So suddenly they say their decision. If both grab the dollar, they lose the game, the dollar. And they are fined $1 each. Assume, when I say $1, assume it's $1,000. So we'll have $1,000, we should decide. If both of us say that I want it, we will be fined $1,000. Not only we don't get anything from the show, we should pay the show. $1,000, okay? If one of them grabs it and the other one doesn't grab it, the person who grabbed it will earn the dollar, right? You see the scenario? It's a hard scenario. If both of them do not grab the dollar, they will lose the dollar. So put yourself in the shoes of the contestant. Should I grab the dollar? Should I be selfish and grab the dollar? But what if the other person is also selfish? Then I will be fined. Should I sacrifice myself and do not grab the dollar? But what if the other person grabs the dollar, is selfish? Right? Yes. So this is a hard scenario. Let's see it in the payoffs here. Consistent 1, consistent 2. So grab, not grab, not. If we both grab it, we are fined. We are penalized. We should pay $1 or $1,000, right? Each of them. If player 1 grabs, player 2 doesn't grab, player 1 wins the dollar, player 2 wins nothing, loses. It's a symmetric game, so it's the other one, 0-1. What about not grab? If both of us not grab, both of us will lose the dollar. It's an interesting show, right? Another variant or another version of this game is that in the TV show Let's Make a Deal, the game is the same as explained, but with a slight difference. What is the difference? If both of them do not grab the dollar, they will split the dollar between each other. So even the scenario got harder. So the player says, should I be selfish or not? If I'm selfish and grab the dollar, what if the other person also grabs the dollar? What if, should I say back off and say I don't grab the dollar? What if the other person grabs the dollar for itself completely? But what if both of us say don't grab the dollar? We are not eager much. We don't have much ego, but it will be split between us, right? It's a hard scenario. What should we do? So, by the way, another difference is that if they both grab the dollar, they lose the dollar, but they are not fined. The show was kind to them. They said, we don't fine you, but you will lose the dollar. Okay? So let's see the payoffs, consistent 1 and consistent 2. If we both grab the dollar, we lose the dollar. We both. If one of them grabs the dollar and the other one not, the person who grabbed the dollar will win the dollar, and the other person will win nothing. It's a symmetric game. What about this? What if we both don't grab the dollar? It would be split between us. You see, these are metaphors of the world. Sometimes it says, be happy with what you have, right? Don't be eager, because whenever you get something, you're getting that something from some other person. Don't get it? So it will be split between you two, right? Do you see the real world scenario? I think this part is showing kindness. So we will see that the Nash equilibria is a plural for equilibrium. Nash equilibria of this game are grab, not grab, and not grab, grab. So the convergence, the rational convergence is that one of them grabs and the other one doesn't grab. If there is a fine for grab, grab. So if we have a fine, so it's -1 and -1, then the Nash equilibrium, we have two Nash equilibria. One of them grabs and the other one doesn't grab. Okay, I think it makes sense because if we both grab, what happens? We will be fined. So I'm scared of grabbing. You might say that not grab, grab, that might not make sense. Why that person didn't grab? Because it was scared of being penalized. Okay. What if there is no fine like this, 0, 0? Then the game has 3 Nash equilibria. Grab, not grab, grab, not grab, grab, and grab, grab. So grab, grab will be also added as one of the Nash equilibria. Okay. By the way, some of these equilibria are weak. So we have weak equilibrium, a strong equilibrium. Okay. These are weak equilibria. We will see. We'll see. I'll explain them to you. So again, in this case, we will have 3 equilibrium. So all of these 3 cells will be equilibrium. So actually, grab, grab might. Sorry. I apologize. Grab, grab is this. Grab, grab might be if there is no fine. If there is no fine, grab, grab will be one of the equilibriums as well, because grab, grab will not be fined. In the TV show, many contestants chose. It's very interesting. Listen, in the TV show, many contestants chose a strategy: not grab, not grab. They were fine, kind to each other, to split the reward. Although that was not Nash equilibrium. Interesting. So experiments showed that people, because they had 5 minutes time to talk, okay, then they always said, okay, don't grab it, I will not grab it, and we will split it. But always the contestants had this in mind: what if that person is bluffing? What if I don't grab it, but that person grabs it? Is lying, maybe they are lying, right? So always they were scared, but they usually didn't grab it, so to split it, right? However, once in the game, some interesting scenario happened. Someone said to the other contestant, I will grab the money, you don't grab it, okay? Otherwise, we both lose the money. Someone directly said to the other person, I'm selfish, don't be selfish. If you are selfish too, we will lose it. Okay. So the other contestant was shocked, because usually they said, okay, I'm not selfish, you don't be selfish, so we split it. But this time that person said, I'm selfish. So that person was shocked and said, let's split it, the money. But that contestant never agreed. Finally, another a more stranger thing happened, that when they showed their decisions, that person hadn't grabbed. So that person said, I'm selfish, don't be selfish, I will grab it, you don't grab it. That person was frustrated, said, why are you selfish? But finally decided not to grab it, because if that person had grabbed it, both of them would lose the money. So that person didn't grab it, but that person who said, I'm selfish, was not selfish, didn't grab it. It was a very complicated scenario. Okay, people were talking about it for days. Okay, so any question? Okay, another important game is Battle of Sexes. By the way, these names are not made up. I didn't make them up. These are in the literature. The Battle of Sexes, proposed in 1957. You see how old it is. A couple of men and woman decide to go out. Okay. The man wants to go to the Fight Club show. The woman likes to go to a ballet show. Okay. So they are fighting where to go. If both go to the Fight Club show, the man gets happy and the woman doesn't get happy. But if they both go to the ballet show, the woman gets happy, but the man doesn't get happy. They cannot consensus. If they can't consensus, what do I mean? It says they can never agree where to go to the same place. They do not go out at all. They will fight and say, okay, let's not go out at all. Okay. I think you see it a lot in the daily lives, right? So man, woman, not necessarily between this, in different scenarios. We see that a lot. So man, fight. So going to Fight Club, going to ballet, going to Fight Club, going to ballet. If both go to the Fight Club, the man gets 2, the woman gets 1. Man gets happy. The woman gets 1. Why? Because the woman still goes out. Right? If they both go to the ballet, the woman gets 2, the man gets 1. Right? The woman gets happy. The man doesn't get happy, but gets 1 because they still went out. But if they can't consensus, they both get 0 because they never went out. They get bored at home. Okay? Interesting game. We see it a lot. By the way, interesting that loss is in this diagonal. Sometimes in some other games, loss was the other diagonal. In this game, loss is this diagonal. Interesting. Right? Another game is the boxed pigs. Boxed pigs. So 2 pigs are put in a box with a control panel at one end and the food dispenser at the other end. Let's consider a box. 2 pigs are there. So players are pigs. And at one end of the box, there is a control panel. The other one is food dispenser. So control panel opens the food dispenser. Okay. One pig is big and dominant, and the other one is small. Okay. So the dominant one, the actions are pressing the control panel or waiting for the other pig to press the control panel. If one of a pig waits for the other pig to press the control panels, they can go to the dispenser sooner to eat more. So it says how much selfish the pigs are, right? When a pig presses the panel at a utility of cost of 2 units, what do I mean? Going toward the control panel costs 2 units, okay? Because they will lose energy. At a utility cost of 2 units, but they get 10 units of food. The 10 units of food are dispensed at the dispenser, okay? So let's consider the actions. Press. What do I mean? They both press, okay? They both press. Payoff of the big pig is this. Let's calculate it. It's 5. Why? The big pig gets 10 units of food minus 3 that the small pig eats, okay? Minus an effort cost of 2 because it pressed the control panel. So gets 10 food minus 3 that the small pig eats minus, so what do I mean? 10 is the total food. 3 of it is eaten by the small pig. 7 units of food is eaten by the big pig. Can you tell me why? Because that's bigger and dominant. And they both went to the control panel. Okay? So 10 minus 3, 7 food. The big pig eats minus 2 because 2 units of going to the control panel. What about the small pig? It gets the 3 units of food minus 2 because of going to the control panel. So 3 minus 2 is 1, right? So that's why 5 and 1, right? Press. What about weight press? What does it mean? The big pig, the first player, waits which means that the big pig not only is dominant, but is selfish. Waits. The small pig, which is very small and slim, goes to the control panel, has to, otherwise if no one goes, they will be hungry. Goes to the control panel. So the small pig presses, so the big pig gets the dispenser first, gets to the dispenser first and eats 9 units, right? So out of 10 units of food, the big pig gets 9 units because goes to the, not only is dominant, but also it goes to the dispenser sooner. The small pig gets its leavings 1 unit, right? Worth 1 unit. But pressing costs is 2 also, right? So the total payoff of the small pig is 1 minus 2, which is -1. Sorry. -1, right? That's why we have 9 minus 1 in this table. Agreed? What about press weight? So the big pig is dominant, but is not selfish. Goes to the control panel. The small pig is selfish, waits. Then what happens? The big pig presses, so the small pig gets to the dispenser first, and eats 4 units. Still, it's a small pig. It's not dominant. It eats 4 units of food. The big pig eats 6 units of food, but pressing costs 2 units. So 6 minus 2 is 4. As a result, they get both 4 for payoff. Can you see that this game is not a symmetric game? Because these two are different. I think it's obvious because one of them is dominant pig, the other one is a small pig. This game is not a symmetric game in contrast to the previous games. What about this weight? So not symmetric game. What about weight? Means that then none of them goes to the control panel. Then no food will be dispensed, so no one eats food. So we'll get 0, 0. They will not eat anything, right? Do you see the interesting thing? And it's not symmetric. You see that a lot in the board, right? Right? The dominant pig. So you see that bullies, right? Bullying in the school and this. So these scenario, the same scenario, right? We see that a lot. Okay. Ranked coordination. Ranked coordination, by the way, this is an important family of games. Okay. We will see that more with more details later. 2 players are the managers of 2 computer companies. Okay. One of the companies sells computers and the other company sells floppy disks. Because this is an old game. At that time, we had floppy disks. Okay. So player 1 decides whether to design computers accepting a small or large floppy disks, because we had a small floppy disks and large floppy disks. So player 1 generates computers accepting small floppy disks or large ones. Player 2 decides to design a small or large floppy disks. Large floppy disks is also more profitable for them. Okay. So let's see. Computer seller, large, small. Floppy seller, large, small. These are the actions, right? If they both say large, so computer gets large floppy and floppy maker makes large floppy, they are both happy. 2-2, right? And we know that large floppy is also more profitable. If the computer seller generates large computer with large floppy, but the floppy seller generates a small floppy, they will both lose because the floppies cannot go inside the computers, right? The other way around is also, it's a symmetric game. If the floppy maker makes large floppies, but the computers get small floppies, they both get -1, they both lose. What if they both make it small? they still are happy, but less happy than making both large because it's less profitable. This is called ranked coordination. I think it's obvious that this is very good, right? Okay. Welfare game. By the way, some of these games might be controversial, but I didn't make them up. Okay, I didn't make them up. So these are in the literature. This is about the Second World War. Okay. No, sorry, I apologize. The next game is about the Second World War, but this is about government. So a social democrat government wants to aid a pauper if he or she is unemployed but looking for a job. You know that social democrat governments pay people who are unemployed, right? I think Canada is like one of them, I guess. In Europe, we also have social democrat. I think Australia is one of them, I guess. But USA is not. USA is liberal democrat, right? USA says whoever has money is better. But social democrats I think is an interpolation of democracy and communism. Okay, socialism is an interpolation between democracy and communism, as far as I understand. So a social democrat government wants to aid a pauper if he or she is unemployed but looking for a job with a condition. It says you shouldn't be lazy and stay at home and expect the government to pay you. Okay. A pauper decides to look for a job or ignores looking for a job while getting the aid from the government. Okay, so the pauper says, should I be lazy and get the income from the government, or should I be honest and look for a job? If the government gives aid and the pauper looks for a job, it is good for both. Both are happy, right? If the government gives aid but the pauper does not look for a job, it means that the pauper is lazy and the government is paying for nothing. Then it is good for the pauper, but not good for the government. If the government does not give aid, but the pauper looks for a job, it's bad for both of them, right? I think it's neither good for the pauper nor for the government, because the government claims to be social democrat. Although looking for a job is slightly good for the pauper, it's better than not looking for a job. Okay. If the government does not give aid and the pauper does not look for a job, it is neutral case. The government doesn't pay, the pauper doesn't, so they are not collaborating at all. They don't care about each other. Okay, so they are both ignorant. Indeed, so let's see, government, pauper. Government pays aid, no aid. Pauper look for a job, not look for a job. So let's see, aid, looking for a job. Best case for both, right? 3-2. Because the government can claim to the world that I'm social democrat, and the pauper is happy also getting income and also is honest. And the government pays, but the pauper is not looking for a job. Government loses, the pauper is more happy because it's not more happier than this, because it's lazy. They're lazy, but they're also getting income. What about it's not a symmetric game. What about government doesn't aid? Government is looking for a job. It's very bad for the influence of the government in the world. The government cannot. It's bad for its appearance in the world. But the pauper gets one at least, because it is gaining something for looking for a job. And in neutral case, they both get 0 and 0. Okay, we will continue in the next session with some other leftover important games, and then we'll talk about Nash equilibrium and dominant equilibrium. We'll see how to find the convergences, equilibriums, and then afterwards Bayesian Nash equilibrium. Okay, thank you. Thank you. Thank you. Thank you. Just give me